Okay, if anybody, by the way, wants to see any of the YouTube videos that I'm making for Zach there, YouTube, I'll just send them to you. They're private links, so I don't think you can search for them. Okay, so we have been working on evaluating correlation functions like this one in an interacting field theory for a scalar field with a quartic interaction. And we have this master formula that relates this to correlation functions of free fields in a free vacuum. Okay, so that formula reads this way. I'm going to leave out the I epsilons and so forth. For now, let me put an I on here in this equation, because these are the interaction picture fields. They're like free fields. And this is the interaction picture Hamiltonian there. That's part of it. The other part is the denominator. And this is a D4Z. We're integrating over all space there. The denominator looks very similar. It just doesn't have these fields down below the exponential. It only has the exponential part. And sorry, this is the Hamiltonian density, so make sure you make that a curly H in your notes. Okay. Where for our particular theory, H sub I is 1/2 pi squared plus grad phi squared plus m squared phi squared. All of this goes with a half. I'm sorry, I'm wrong. That's not part of HI. H interaction doesn't include this part in the interaction picture. It only includes the interaction term. My mistake. It just includes the lambda over 4 factorial phi I of x, the fourth power. Okay, so now in principle, this is a complete, this formula tells you everything about how to compute this. We take this, we expand the exponentials out in powers of lambda, and we calculate the correlation functions, the free correlation functions, using Wick's theorem from last time to the desired accuracy. So, but that doesn't make it easy. Yeah?
And so lambda will depend on the situation?
Well, lambda is the coupling constant. And this term, for different theories, it'll have different forms, okay? Some theories, the coupling constant we might call G or something, but in general, this will always be a polynomial in phi. And so when we expand the exponential, we'll just get a bunch of time-ordered products of free fields, which we can calculate. Okay? So last time, we worked out what the numerator of this thing was. We didn't do the denominator yet for up to order lambda. And let me just write that out. Numerator to order lambda, just review what we ended up with, because I did it kind of fast at the end. Okay, so the numerator, let's call it n, is 0 times time-ordered phi x, phi y. Now, I'm just going to leave the interaction picture eyes off, okay? If you see a free vacuum here, that means I'm talking about interaction picture free fields. And then the exponential we expand out as 1 minus I times lambda over 4 factorial integral of phi of z d4z to the 4th power. And there will be, the next order term will be minus I lambda over 4 factorial squared integral phi z to the 4th, phi z prime to the 4th, d4z prime, and so forth. Okay? And we make it clear, all of this is inside of the time ordering symbol. Okay? I think I better move this back a little so Zach can see everything. Okay. Good. Now, where are we? Okay. So let's continue. That's 0 times t of phi x, phi y, 0, taking the first term with a 1 there. And we represent that diagrammatically by a line running from x, or y to x in this picture. But it has a meaning as a particular function of x and y. It's df of x minus y. Now the next term looks like this. I'm going to pull the integral over d over z out in front. And I'm going to take phi z to the 4th power, and I'm going to be very pedantic and write it out as 4 factors of phi to the z. And I'll ignore the other stuff. So how do we evaluate this time-ordered product of 6 free fields? Well, we had the answer last time, which is you draw all of the contractions of phi x, phi y, phi z, contracted with phi z, contract the other two phi z's with each other. That's one type of contraction. And the other type of contraction that we can get is if you contract a phi x with a phi z, sorry, Zach, this, phi x goes with phi of z, phi of y goes with another phi of z, and then we have 2 phi of these z's left over. And these are basically the only 2 types of contractions you can have. Either x is contracted with y, or x is contracted with one of the z's, and y is contracted with another of the z's. Okay? This particular first type of contraction gives us df this first type of contraction gives us df of x minus y df of z minus z squared. And the second set of contractions gives df of x minus z df y minus z df of z minus z.
So, can we just write as df0?
Well, for now I wanted to write it as z minus z just to show you where it came from. But yeah, it's df of 0. The problem is that's a singular object. It's infinite. And, we're not quite sure how to deal with it yet. Okay? Now let's see, how many ways are there of doing this? There's only one way of connecting phi of x to phi of y. But there are a total of 3 different ways of pairing up these 4 phi of the z's. Right? Pair them like I did here, or you can take this with the third and the second with the fourth, or you can take this with the fourth and the second with the third. So 3 possible contractions here. So really I should multiply this result here by 3 for this type of contraction. And for the other type of contraction, well, phi of x can contract to 4 of the phi of z's, and then phi of y can contract to one of the 3 phi of z's left over. So there's a total of 12 here. In general, the combinatorics for figuring out these factors can get rather complicated, but there's some simple rules that will help you remember how to do that. So anyway, I'll now erase these here, and well, the third way of thinking of this set of contractions is as a diagram, where you contract x to y like so, and then you contract z to itself, and you have another contraction of z to itself. Okay? So this part of the diagram represents the Feynman propagator between y and x, and this figure 8 diagram represents 2 contractions of z with itself, of phi of z with itself. Down here, the diagram that represents this term looks like that. Okay, so far I'm just reviewing what we talked about on Thursday. But, basically, this is what all of our Feynman diagram calculations boil down to, so I thought it would be useful to say it twice. So now what I want to do is I want to go to the next order. I should say this isn't the whole amplitude. I also need to have this minus I lambda over 4 factorial integral d4z of that thing. So let's evaluate the next order in this perturbative expansion. That's order lambda squared. Okay, I'm going to write that out as a bunch of diagrams, and basically the rule is we just take all diagrams that we can make that have 2 vertices, meaning two places where 4 lines meet, like that. Okay, and it's going to come from this term here. It's going to have, well, 5x, phi y, and then 8 more factors of phi from the expansion of the exponential. Okay? And 1 vertex at z and 1 vertex at z prime. So we're going to have diagrams, for example. So this is the numerator at order lambda squared. First of all, we're going to have this factor out in front. I'm not even going to write the factors. I'm first going to write the diagrams, okay? It's easier to remember all your terms here if you do it using diagrams. So we'll get a diagram, for example, from x to y. That looks kind of like this diagram here, except we can just put two figure eights. There's one at z, and here's another one at z prime. And another thing we can do is go from x to y again with nothing happening in between, and then have a triple scoop here. That's called a triple scoop diagram. It's an ice cream. Again, with a vertex at z and z prime. Okay. Anybody want to suggest another diagram? Everybody tell me one diagram.
From x to y with two z's in the middle.
Okay. We can do that. Is that what you meant?
Yeah.
Okay, any other suggestions? Why doesn't everybody try to write out all the diagrams in your notes and then look up at the board and see if it agrees what I write down? Okay. No, I did that already. Okay, I get a total of 7 different diagrams. Okay? This, by the way, is called the basketball diagram. I just made that up. Okay? These are all the different ways of contracting these 10 phi operators together in distinct ways.
Now, have you not labeled, like for, I guess, the third there, with the line and loop and then the double scoop? Are you not labeling them Z and Z prime? Because it doesn't
Oh,
matter.
I'm just tired of labeling them.
But it doesn't matter which one's Z or Z prime.
That's right. Actually, it's a dummy variable. So in the integration, when we expand the exponential, there's going to be a factor of, I didn't put it in here, I forgot it. 1 over 2 factorial. That makes sure that we don't double count. I mean, it's coming from the exponential, but it has the effect of saying, don't double count having a z vertex here and a z prime vertex over there. Don't count that. And switching the z and z prime as two separate diagrams because they're not doing anything different physically. So you can see things get very complicated already with two vertices, and you can imagine if you had 4 or 5 vertices, it would just be completely unmanageable. And the number of diagrams actually at each order of perturbation theory grows exponentially. So at 4-loop level, there are hundreds of diagrams. 5-loop level, there are thousands. It's not loop level. Fourth order in perturbation theory or 5th order. The number increases very rapidly. Now, each of these is associated with a product of Feynman propagators. So, for example, the first guy would be df of x minus y. Now we have to put in all the factors of lambda and I and integrals over z and z prime. And so the first diagram here is df from x to y, and then df of z minus z, and df of z prime minus z prime. And then there's going to be a symmetry factor as well, which corresponds to all the different possible contractions here. Each of these we saw you can make in 3 different ways. Okay, so we're going to have a symmetry factor. Well, we're going to have an extra factor corresponding to all of these contractions of 3 for each of those diagrams. So instead of factor 3 in front of here, we'll get 9. I'm not going to go through all the rest of these here, okay? But that should give you enough information to figure out how to write these down and how to do the first homework problem. Let me say a couple more words about symmetry factors now. So for that first diagram, I already erased it, but we had a total numerical factor of 1 over 2 factorial, 1 over 4 factorial squared, and then 3 times a 3, okay, times okay? And so, and each of these is going to have some numerical factor like that in front of it. Okay? So I'm going to define this numerical factor for a given diagram. I'm going to call it 1 over s. Because generally, it actually is going to end up being 1 over an integer. Okay? So in this case, it's 1/2, 1/24 squared. 3 makes each 1 over 4 factorial into a 1 over 8. So this is 1 over, am I doing this right? Yeah, it's 1 over 8 squared, 1 over 64th. And this 1 over, over 2 factorial gets how does that happen? It gets canceled.
Where's the
Yeah?
1/4 factorial squared come
That came from, sorry, this shouldn't be here.
from?
Minus I lambda squared. It came from the lambda. Each
Okay.
4 factorial came from the lambda. Okay? Yes, okay. The thing is, there's a 1/2 factorial here, but really, yeah. But the reason I shouldn't write that here is because I get a diagram that looks like this, and I get another diagram that looks like that, with the z and the z prime interchanged. So when I include the fact that there are these 2 types of diagrams with the, or 2 diagrams with these integration points interchanged, I should cancel that 1/2 factorial. I already said that, but basically what it means is in the amplitude, there's no 1/2 factorial anymore. And in something with n vertices, we forget about the 1/n factorial because you could interchange the vertices, the points labeling each of the vertices in n factorial ways. Okay? So this is what's left over finally, is 1/64 times all of this stuff. Okay? You can think of that as 1/8 squared, where you get a 1/8 symmetry factor for each of these figure 8s. Now this is the way to remember this. You'll just have to convince yourself by doing some practice on the homework problem that it is true. But one easy way to remember the symmetry factor associated with a given diagram is to look at all of its symmetries. So for example, let me just draw a few diagrams here and say what their symmetry factors are. There's a diagram we've seen. You remember we said this had a factor of 12. There were 12 ways of getting this contraction. And that, when you multiply that by 1/4 factorial, you get a 1/2. So in this case, the symmetry factor, make a little table diagram, symmetry factor. So in this case, the symmetry factor is 2, because there were 12 possible contractions giving this, and we divide by 4 factorial for the vertex. I'm sorry, 1/2 was that, so the symmetry factor is 2. That's why. The figure 8 diagram we've seen has a symmetry factor of 8. And that's because there were 3, and that's kind of nice. It's the figure 8 has a symmetry factor of 8, right? 3/4 factorial is 1/8. Of course, if you evaluate this diagram, you get infinity, which is 8 on the side. Okay, one more example would be this diagram here. Now here, symmetry factor of 2, the way to remember that is this diagram actually has a symmetry of order 2, which is just flipping that circle in the middle. You've got to keep the endpoints fixed, but you can flip the circle, flip the loop. so that's two possibilities. Symmetry of order 2, and that gives you a 2. This one here, you could flip the top loop, you could flip the bottom loop, or you could interchange the top and the bottom loop. So the total symmetry is of order 2 times 2 times 2, which is 8. In this case, you could interchange the top, middle, and bottom lines in a total of 3 factorial ways, 6 ways. So this symmetry factor is 6. So you get the idea. That's how you calculate symmetry factors. Okay, now we have all the information we need to, in principle, write down any term in this perturbative expansion. Okay? And let's summarize those rules for the perturbation theory. So, at order lambda to the n, form all diagrams with n vertices and 2 endpoints, x and y. We build these diagrams out of lines and out of vertices. And for each line, which we call propagators, because they propagate a particle from x to y, you associate a Feynman-Green's function, which takes you from x to y. For each vertex, which looks like this, we associate a factor of minus I lambda times integral d for z. I'm not including the 4 factorial and put all the numerical factors together at the end. Just want to make sure we're still recording. Good. For each, this is kind of a stupid rule, but this third one, but we'll see that it gets generalized later. For each external point, like this, x, we associate a factor of 1. And finally, we have to divide each diagram by the symmetry factor. Yes. Those are called the Feynman rules. Okay? That set of rules encodes everything you need to know about calculating the nth order in perturbation theory of this particular scalar field theory. For any quantum field theory, they'll be generalized, but not very much. The vertices might be more complicated or just different. You might have vertices. If you had a phi to the 7th power, you'd have a vertex in your interaction Hamiltonian. You would have a vertex with 7 lines coming into it. Okay? If you had a different type of field than our scalar field, like a photon field, you would have a different propagator here. But the basic logic is the same no matter what type of field you're dealing with. Okay. Um, so that's great, okay? It's not the end of the story, though. One problem is that a lot of the integrals you end up with, like the integral d4z of df of 0, are infinite. So, so problem number 1. df of 0 minus 0, or z minus z, is integral d4p over 2 pi to the 4th. There's e to the minus ip of dot z minus z, and then I over p squared minus m squared plus I epsilon. Of course, if z equals z, which it does, this factor is 1, and that integral d4p over something like p squared is obviously divergent. As p goes to infinity, this thing scales like p to the 4th, the denominator is only like p squared, so it's actually diverging like well, it's what we would call a quadratic divergence. 2 powers of p here, 4 powers of p here, 2 in the denominator, net of 2 powers of p. Okay, so this is divergent. And problem number 2 is that the integral with respect to z of df of z minus z, df of 0, is integrating a constant that happens to be an infinite constant, and that diverges too. Okay? So this is actually the integral d4z gives us a factor of the volume of space-time times df of 0, which is also infinite. There are other infinities contained in these expressions. We'll deal with them later, but these are 2 of the worst ones. Now this one here is a simple interpretation for why we get this in infinity proportional to the volume of space-time. It's because this diagram here, which basically means that you start at point z, and a couple of particles pop out of the vacuum at z, and each of them goes around a loop and comes back to z, and then they get soaked back up into the vacuum. They get annihilated back at the same space-time point where they were created. It's kind of a little bit of a strange concept there, but the reason we get a volume of space-time factor is this could happen anywhere in space-time. Z could have any value. You could have particles popping out of space and back into out of the vacuum and back into it anywhere in the world. And so we get a volume of space-time factor here to indicate that this amplitude is equally likely anywhere. It's not that these infinities are any surprise. I mean, we're trying to do quantum field theory, which is quantum mechanics with infinitely many degrees of freedom. So we expect that unless we're very careful, when we add up the contributions of infinitely many degrees of freedom, we're going to get infinite answers. So let me explain, at least, what happens to these infinities here. So, these divergent factors arise from diagrams with disconnected pieces. Like, for example, this diagram had a disconnected figure 8 that wasn't connected by any line to x or y. Okay? Other terms of this type, which are disconnected, which end up giving you this type of problem, are, for example, the double scoop, two double scoops or two figure 8 diagrams, disconnected from the propagator from x to y, or this basketball diagram. And so forth. Then there's, if you like, other disconnected diagrams. In fact, almost all of the diagrams we wrote down at order lambda squared were disconnected. This diagram will also have, there will also be a bunch of diagrams connected to this single scoop diagram. Or disconnected diagrams like that. Identity, right? One more of these down. And so forth. Other like connected diagrams times disconnected diagrams. So each of these here is a factor of df x minus y, then times the contribution from the disconnected pieces. So symbolically, I can just take this first factor from x to y. Each of these is going to have a Feynman propagator from x to y in it. And say the first row here, I can write in this way. That's the first row. All this means is this is df x minus y times df of, well, this would give us integral d4z df of z minus z squared, symmetry factor of 8, so we have a 1/3 here, or 1/8, I mean, and so forth. Right? I'll erase that. And go on to the next line. And I can again factor out this connected piece from the disconnected parts of each of the diagrams. You begin to see the pattern. The point is, for any connected diagram like here, like this, I can always generate a bunch of diagrams by adding disconnected pieces. And instead of all these disconnected diagrams, let me give them a name. I'll call them vacuum diagrams. Sometimes they're called vacuum-to-vacuum diagrams. They just represent amplitudes for particles to be created and then annihilated out of the vacuum without interacting at all with the particles we're trying to observe over here at x and y. So the point is, when I write down infinitely many of my Feynman diagrams, the vacuum diagrams can be factored out. Okay. Let me write that down. The last line, I'll write the connected diagrams first. Just write, let's say, connected diagrams. And then they all get multiplied. Each of them gets multiplied by the sum of these vacuum diagrams. So the point is the vacuum diagrams factor out. They factor out over the whole diagram expansion. Now if you remember, what I've been evaluating here is this numerator. Oh, sorry. Phi x, phi y, exponential minus I, integral d4z, lambda over 4 factorial phi fourth, 0.
I think we should actually I in front of all variables.
Extra what?
1. Because the contribution for.
Oh, you are right. There
we
is
just
also
add 1
a.
there.
You're absolutely right. There's a 1 here. 1 is kind of a trivial disconnected diagram. It doesn't do anything at all. But we can still include that here to get the complete Feynman diagram. Some very good looking things. Okay. So that's an evaluation of the numerator. I still haven't told you how to evaluate the denominator. In principle, we have to go through this whole procedure again and expand that out in powers of lambda and write down all the diagrams. So let's talk about the denominator. So the denominator what happens when we expand this out? This is very similar to the numerator, except there's no phi at x and phi of y. So what we get when we expand this out are diagrams that don't have endpoints x and y in them. We get diagrams like, well, we get a 1 from the first term in this expansion of the exponential, going from 0 to 0. And then the next diagram we get at order lambda, looks like this. And the diagram after that, which has no external lines, we get this, and we'll get another lambda squared diagram looking like this, and so forth. In other words, we get exactly the same set of vacuum diagrams. They're vacuum-to-vacuum diagrams. They take us from the vacuum back to the vacuum. The same set that we got here for every diagram in the numerator. And that's absolutely fantastic, because it means the denominator here is canceling out all of these vacuum-to-vacuum factors, all of these horrible infinities. And it cancels all the vacuum diagrams, all the disconnected, I call them vacuum subdiagrams. Because each of these is a part of a diagram. In the numerator, so the final result is we don't have to calculate any of these divergent things. They cancel. It's like a normalization factor, this denominator that cancels this infinite normalization of all the diagrams in the numerator. And we are left with after cancellation, we're left with the final answer for our calculation of this interacting correlation function is equal to the sum of connected diagrams. Like this one from x to y, like this one here. It has a loop in the middle, like this one, and so forth. So that drastically reduces the number of diagrams we have to calculate. It drastically reduces the number of infinities we have to deal with. We're still going to have infinities here and there, but they will be infinities that we can manage.
So the denominator
What's the
lead
question?
them to be 1.
What
The
is
summation of word graphs, the denominator, vacuum impactation value, the first line.
here?
Yes, it can be 1 or not.
The sum of these?
Yes.
No, it's infinity. It's really bad infinity, in fact.
Okay, so in the interaction here, it just give us the infinity vacuum impactation value.
This would be infinite. Each of these diagrams would give an infinite contribution to the total interacting correlation function. But they cancel. All these these diagrams all cancel exactly with those diagrams down there. With the diagrams in the numerator. These diagrams are also giving infinity. But it's exactly the same set of diagrams, of vacuum diagrams, that we get in the numerator that we find in the denominator. Factors is the sum of vacuum diagrams factors out from every diagram. Okay, I'll write this just a little more explicitly. Okay, so this is the numerator here is the sum of connected diagrams times vacuum diagrams. And that's just what we figured out down here. Okay, we wrote the numerator as a product of the sum of connected diagrams times this sum of vacuum diagrams. The denominator is the sum of the same set of vacuum diagrams. And the point is these cancel. So you never have to compute one of these vacuum diagrams.
What's the meaning of this infinity in these vacuum diagrams?
Well, it's an interesting question, yeah. Basically, we've already encountered this infinity, a very similar infinity, when we calculated the Hamiltonian for a scalar field. We got this infinite term that actually was like a delta function of 0. Okay, the delta function of 0 is the integral d for x of e to the I p dot d for p e to the I p dot x at p equals 0. I'm going to write it this way. I'm going to write it as a position space delta function, but it doesn't really matter. When momentum space delta function. When p equals 0, you can see this just gives you a factor of volume of space-time. Okay? That's because you could have that 0-point energy for a harmonic oscillator, 1/2 h bar omega. You had a harmonic oscillator at every point in space-time, and you added all of those 0-point energies up over all space-time, you've got a factor of volume of space-time. Okay? So you can think of these as the perturbative corrections in this interacting theory to that calculation of the energy of a free scalar field. Okay? This 1 here, when you set lambda equals to 0, ends up reproducing, I didn't explain that very well, why it gives you a delta function, but it does. It gives you a delta of 0. Reproducing the free energy of a free scalar field. And then there's also interacting energy as well. 1/2 h bar omega gets modified when you go to an anharmonic oscillator by something of order lambda, but it's still going to be integrated over all space, and it's still going to give you an infinity. Okay? So this is actually computing, and maybe I can explain that, I'm not prepared to at the moment, but it's computing the energy, the corrections in powers of lambda to the energy, vacuum energy of space-time. That's the energy of the 0-point energy of the scalar field. And effectively what we have done by canceling these, it's more or less equivalent to what we did before, which was to shift the 0 of energy. Just throw the 0-point energy away. Point is, the 0-point energy physically doesn't couple to anything we can measure. We can measure this amplitude for a particle that starts at y to end up at x, but it moves from y to x without having to deal with and interact with any of these vacuum diagrams here. It just sort of goes straight through. Okay, good. Now, so that's our result for now. As I said, it reduces the number of diagrams dramatically, so in calculating this two-point function, instead of calculating at second order, having to calculate 7 diagrams, you actually only have to calculate 3. And at higher orders, it makes a much bigger difference as well. Now, I've given you everything you need in principle to calculate all of this here. But to actually do it in practice, it's often more convenient to work in momentum space. Okay? The hard part of calculating all of these will be doing the integrals over d4z. We have a lot of integrals, 4 integrals to do for each vertex factor. So in these 2-loop diagrams, you have to do a total of 8 integrations, and it turns out to be much easier to do those integrations in general in Fourier space, in momentum space. So let me talk about how to discuss Feynman rules in momentum space. So first of all, one thing that simplifies in momentum space is the propagator. So in position space, df of x minus y, let's write it one more time, is an integral over momentum space. So e to the I p dot x minus y times I over p squared minus m squared plus I epsilon. So it's a Fourier transform of this momentum space propagator. And so the Fourier transform of this thing is therefore I over p squared minus m squared plus I epsilon. So for one thing, the propagator functions are much simpler in momentum space. It's just 1 over a polynomial in P, a quadratic polynomial. So in momentum space, what we can do is we can give a set of Feynman rules, and we can think of, when we have a propagator, instead of thinking of it running from x to y, we think of it in momentum space. We think of it as having a momentum p flowing through it. Okay, really, it is just like position momentum duality here. We can either think of this particle as having a definite position as it moves from x to y, or we can think of it as having a momentum. Just 2 ways of representing particles in terms of position or momentum eigenstates. Okay, the vertices now are going to be a little more complicated. What we'll do is we'll put all these Fourier factors in with the vertices. Okay, so for a vertex, we're now thinking of having momenta associated with each of the lines. So I'll say this is P1, P2, P3, and P4. And just for convention, let's say the momentum is, let's orient the momenta so they're flowing inwards towards that point. So we want to account for these exponential factors, these Fourier transform factors. And you can see that each line from x to y is going to have an e to the I p dot x on one end, and having an e to the minus I p dot y on the other hand if you have a momentum p flowing through that line. Okay, so if we associate these factors here to this propagator line here, then what we should do if we have a bunch of momenta flowing into a point z is we should put in addition to the usual integration over z, we should put a factor of e to the, let's see, if they're flowing towards z, we get an e to the minus I p1z, e to the minus I p2z, e to the minus I p3z, e to the minus I p4z. Those are all four-dimensional Lorentzian products. And of course, there's a factor of minus I lambda out in front. And we can do this integral actually, right? Because this is e to the minus I p1 plus p2 plus p3 plus p4 dot z. What is that equal to, that integral? It's a delta function. It's a delta function actually with a factor of 2 pi to the fourth in front. Okay, so that's what we associate to each vertex factor. It has a very nice physical interpretation. What it says is the sum of all the momenta flowing into this point z has to be 0. Okay, so if you have P1 and P2 flowing in, then you better have P3 and P4 flowing out. You have the same amount of momentum flowing out through P3 and P4. Okay, so what this does is it enforces momentum conservation at the vertex. Well, the momentum conservation delta function. So I'll say this is the first Feynman rule in momentum space, is this factor of df of p for each propagator. For each vertex, we get a delta function. And for each external point, now we have to end up at, when we get back out to the external point, if it's x, then we need to impose the x dependence. So external points give a Feynman rule of e to the minus I p dot x. And that is if the momentum is flowing towards x. And then when we do, we integrate over all momenta. And that has the effect, when we integrate over momenta, it has the effect of imposing momentum conservation at each vertex. So some of these integrals are very easy to do. We just integrate delta functions. Okay, so that imposes momentum conservation at each vertex. And you can do those integrals, the momentum conservation integrals, without even writing down delta functions. You just make sure you choose your momenta so that the some of the momenta flowing into a vertex is conserved. You'll be left with some additional undetermined momentum integrals at the end. And finally, you divide by the symmetry factor of the diagram. And that's how you do a general Feynman diagram, and evaluate a general Feynman diagram in momentum space. And it gives exactly the same answer as our position space Feynman rules, but it's just easier to calculate. Okay, that's it for today. A learning assistance email or
From Libya, the latest